Let us try to solve this problem. They say that there is a straight wire which does not have a negligible cross section. It has got a cross section of radius A. This is the way to show that, right? So what we do, we show two parallel lines. They could be a square cross section or a circular or a triangle cross section, right? So the way to show the cross section is to draw this view, draw the cross sectional view, draw the cross section on this, right? So calculate the magnetic field in the region R less than A, and then after having done that, you do it in R greater than A. Okay? Now let us try to understand. So we have a cross section which looks something like this, right? So we have a cross section of radius A. Okay. Now, or I should have drawn it slightly bigger. Let us say this is the cross section. This is the cross section which is circular. Which is circular, right? This looks a better circle. Which is circular like that, and has a radius of A. Okay, it has a radius A here, right? And I want the magnetic field within this, right? I want the magnetic field within this when the radius is R, right? When the radius is R. So what I'm trying to do is to take a radius small r, okay, and try to find out what is the field at this point, right? Correct? Now we see that if the current is uniformly distributed, so if the current is uniformly distributed, if the current is uniformly distributed, then what happens? Then pi r square area, pi a square area includes I amperes, right? So 1 unit area will include I upon pi a square amperes, ampere per meter square of current, and pi r square area will include 1 upon pi a square into pi r square. Now that gives us I into r square upon a square amperes of current. Okay, so this whole thing, and we had said that if we find the B dot dl, it has to be as if there is a membrane spread over this, and whatever current pierces that membrane will be our current. Correct? Now let us try to understand something about the direction of B. Okay, what can be the direction of B? Okay, what should be the direction of B? The current now, if you can see, is kind of coming out of it, right? So current seems to be coming out of it. because the current flow is something like this, something like that, and you are looking at it from here. So current is coming out of this cross section. Okay, it's coming out of this. So current is directed outward everywhere, right, towards us. Now what? Now what do we do? No, what will be the direction of B? Anti-clockwise? No, we are looking from this side. We are looking from this side. Here. This is how you are looking at it. Okay, what should be the direction of the field? The direction of the field will be along this direction, along the direction in which we traverse, right? Because this can be thought of to be made up of very small filaments, right? Very thin filaments, all carrying a current in the outward direction, and all of them have a tendency to create a field that is tangential to this, right? Not all, maybe something here that does not create a tangential field, but then let us try to understand. Let us say if it is at this angle here, say kind of like that, okay, then what is there if you look at it like this, okay, to the left of this line and to the right of this line you have got identical things. So why should some make it pushed like that, and some this will not kind of pull it like that? You understand? Why should it be making an angle like that? Okay, more so because this is cylindrical symmetry. This is a cylindrical symmetry. So what makes it align like that? It won't be like that actually. It will actually become tangential. Now if it is tangential and its value everywhere will also be the same. Understand? Because either you are standing here or you are standing here or you are standing here, you're not be... Why tangential? That's what. See, this has got, say let me make a bigger version of this. There is a strand. See, let us divide it in two parts, like, right, two semicircular parts. Now there is a strand here, correct, and there is a corresponding strand here. Both of them are carrying equal currents. Now in what direction will this create a field? This is its radial distance. This will create a field in a direction which is 90 degree to that by itself, right? I is towards us, IDL is towards us, R is this. If you do that, the vertical is towards us, and if you do this, then it will be tangential, right? IDL cross R. Fine. Now let us try to understand this. What about this? What about this? This is also 90 degrees. Now let us try to think. What happens to their sum? Yes? How about this current? No. Wait. This field will not be like this. What will be the direction of this field? Right hand thumb rule. If you put your thumb in the direction of the current, which is outward, your fingers will curl like that. So you will be making an angle of 90 degree with respect to this, right? So what happens? Their vertical components. The vertical component is like that. The vertical component here is like this. The vertical components will cancel while the horizontal components will add up. You see that? So the net thing will be tangential. You see that? For this, the right hand rule tells you that it will be like that. No?
You should use right hand rule both using bias over to
No, bias over time. They give you the same direction. They are giving you the same direction. Ideal is here, cross R is there. See? Ideal is in this direction, right? And R is in this direction. So you understand? R is actually perpendicular. So this will be perpendicular to this, no? See, your current element is coming out of this, right? So ideal is outward. Now it's kind of, how do I show outward? Outward, let me show like this. Okay, this is out of the page, right? And R is something like that. This is vertically up. I'm not able to show it here, but this is vertically up, right? This arrow, this. Now ideal cross R, try to take this vertically arrow pointing towards you and try to align it with this R. What is the direction? The direction is actually perpendicular to this. Okay? It's like that. Is it not? So it is ideal cross R is something like this, which I have shown here. Correct?
if both will be there, the same direction will get added up.
No, this is in this direction, this is in that. And together the verticals cancel and the horizontals remain. So they give you a tangential field. No? We don't get that? No? Should I zoom this? Should I zoom this? So let us try to zoom that. You understand? You understand what I did? Let me draw a bigger circle and show it to you once again. What I'm trying to do is, okay, this is the symmetry line that passes through the center, and I have say I have a current element which is like that, corresponding to which another symmetrical current element is like that. Now these are the R vectors, right? Okay, and let me make them broken. Okay, now the field due to this is perpendicular to this. You see that? So it is that. And the field due to this is perpendicular to this in this direction. Now if you look at this line, right, then I am trying to resolve these vectors. So there is a component, a horizontal component of the upper vector like that, and of the lower vector like that. I'll use different colors, right? So the lower vector is shown in magenta, right? And then this has the vertical component something like that, and this has the vertical component pointing down like that. Okay, and these vertical components will cancel. Okay, so these vertical components will cancel, and what you're left with is a horizontal one which is tangential. Now for every element, any current element on this side, you have a corresponding current element on this side, and it will always have the vertical components getting cancelled and the horizontal one remaining. So if you find at this point, it is due to the sum of all these elements, and they sum to a horizontal component, and that too in this direction. So at all points B will be tangential. That is number one. Okay, so at all points on the circumference of radius r, at all points on the circle, on the circumference of the circle with radius a, with not with radius a, we are talking about radius r, right? Radius r, the field is, first of all, the field is number one tangential to the circumference. And number two, equal at all points on the circumference. Equal at all points on the circumference, right? And why equal? That too you can fathom. See, whether I'm standing here and I'm taking these elements, or I'm say standing here and I again start doing the same thing, no? I again start taking the same kind of elements, right, on the left and right of the dia. So they'll sum up to the same thing, right? So this. Now what? Let us apply the Ampere's circuit law. So by Ampere's circuit law, what happens? B dot dl, and this is our loop where we are traversing, right? This is the loop where we traverse. So B dot dl is equal to mu naught into I enclosed. correct? It's mu naught into I enclosed. Now what is the enclosed current? This we have found out to be this. So and B is a constant. So B into DL, and DL and B are always at an angle 0 degree, so they point in the same direction. That is mu naught into I into R square upon A square. Now B being a constant can come out of the integral, so I am left with dl. Cos 0 is 1, so that is mu naught I R square upon A square, and this becomes 2 pi into R is equal to mu naught, is equal to mu naught into I into R square upon A square. So B is equal to mu naught into I R square upon 2 pi R into A square. Now R cuts this R, and we get B as mu naught I R upon 2 pi A square. Okay. What when I am external to this wire? Say I am standing here. When this is for R less than A. How about for R greater than A? Right? For R greater than A, we again have the same thing by the same logic. So you have whole of this wire like that. Whole of the wire like that, and this is your radius A, and say you are standing somewhere here, right? Again by the same logic you will find that the field is tangential. So the field is number A, tangential, okay, and say this is the point at the radius R, and second, equal at all points on the circumference. Circumference of radius R on the Amperian loop. In the same manner that you call that a Gaussian surface, we call this N R of the Amperian loop. Everywhere, so it's kind of this. Of the Amperian loop, right? Now what happens to the B dot dl? Let's try to see that. So B dot dl is mu naught into I enclosed, which is B into dl into cos 0 degree, is equal to mu naught into I. Now it encloses the full current that is being carried by this whole wire. So the I enclosed here is I itself, right? And B remaining a constant, cos 0 being 1, so B comes out, dl is there, this is mu naught into I, so B into 2 pi R is mu naught I, so B is equal to mu naught I upon 2 pi R. So this is when you are out of the wire, right? Now let's try to plot this B versus R. Okay, let's keep both the expressions here in front of us, right? So what happens here is, let's say we draw this is R and this is B, right? So what happens when I am within and going out? Then B versus R, if B is represented by Y, this whole thing is a constant. Okay, if B is represented by Y and this by X, because this is being represented on the X axis, then you can say this is Y is equal to mx, which is the equation of a line that passes through the origin, right? Y is equal to kx format. So it kind of increases, and k is positive, so it goes like that. Depending on these values, the slope will change, right? What is the slope? This tan theta is m, and this m is what? This m is mu naught I upon 2 pi a square. So this m is that, tan theta is that, so m is that, right? Higher the value of m, greater is this value, theta. And it attains a value what? If I put r is equal to a at this point, right? If I put r is equal to a, then it becomes mu naught I by 2 pi a. So here the value is mu naught I upon 2 pi a, right? This value b is that. Get that? And after that, it is y is equal to, say this is some constant k upon x. So it is xy is equal to k, which is a rectangular hyperbola. Okay, so it takes a shape something like right. Now for this won't hold. Why? Because in this region it is this which holds. Okay, so this part is useless for us. You see that this part is useless for us, so I erase this. So the part that interests us is this. It gradually goes to 0. Now if I put r is equal to a here, it gives me mu naught I by 2 pi a, which is nothing but this, which is the same. So ultimately what happens? At r is equal to a, the value attained is mu naught I by 2 pi a, that is given by both the formula, right? And the graph looks something like this. Get that?